Have you ever just looked at the world and wondered how we make sense of it all? I mean, think about it. From population growth to the simple path of a thrown ball, reality can seem super, super complex. But what if I told you there's a kind of universal language we can use to describe it, understand it, and even predict what's going to happen next? Well, today we're going to dive into that language and the amazing tools it gives us. So here's the fundamental challenge for pretty much everyone, whether you're a scientist or just, a curious person. We're all trying to find some kind of order in what often looks like total chaos. We're surrounded by things that are constantly changing and evolving, and our goal is to figure out the underlying rules that make them tick. Just think about the speed of a falling object. It's not constant, it's changing every single second. Or what about the world's population? It doesn't just grow, it grows at a changing rate. These are incredibly complex, dynamic systems. But, and this is the cool part, if you look closely enough, you start to see patterns. That falling object doesn't just speed up randomly, it accelerates in a really predictable way. The population doesn't just go up and down, it tends to follow a curve. Our job is to spot these underlying patterns. Because once you understand the pattern, you unlock the real magic, prediction. Suddenly, you can predict when that falling object is going to hit the ground, or you can make a pretty good guess at what the population might be in 20 years. This is the true power we did from finding that order in all the chaos. Right? So that's the million-dollar question, isn't it? How do we build a bridge from something happening in the real world to a neat and tidy equation that we can actually work with? Well, the answer is through the art of what we call modeling. And that bridge I was just talking about, that's exactly what a mathematical model is. It's our way of creating a simplified version of reality that we can then poke and prod at using the precise tools of mathematics. Okay, so here's the crucial thing to get. A mathematical model isn't the real thing itself. It's a description, kind of like a blueprint for a building or a map of a city. It's an equation or a function that's designed to mimic the behavior of the real thing, which lets us study it without all the messy real-world complications. And this quote just nails the central challenge of modeling. You're always trying to strike this perfect balance. If you make it too simple, your model is basically useless. But if you make it too complex, you can't solve it. The real art is finding that sweet spot right in the middle. This whole process is actually a continuous cycle, a loop. First, you formulate a model, maybe based on some data you have or just the laws of physics. Second, you do the math, you solve it. Third, you have to interpret your results. What do these numbers actually mean back in the real world? And finally, the most important step, you test your predictions against new data. If they don't match up, no big deal. You just refine the model and start the cycle all over again. Okay, so to build these models, we need a toolkit, right? A kind of catalog of essential functions that are going to be our building blocks. Let's start with the most basic shapes that can help us describe change. Let's start simple. Imagine the temperature dropping by the exact same amount for every 1,000 feet you climb a mountain. Or maybe the cost of something goes up by exactly $2 for every item you make. This is change at a constant, steady rate. The answer for this is a linear function. You've probably seen it, y equals mx plus b. Its graph is just a simple straight line, but the most important piece of it is that m, the slope. That slope is the rate of change. If the slope is 3, it means y is increasing 3 times as fast as x. It's the simplest, most direct way to model change. But, of course, most things in the world aren't that simple. The rate of change isn't always constant. A car doesn't just go 60 miles an hour instantly, it accelerates. A company's profits might grow faster and faster over time. The rate of change itself is changing. So what do we pull out of our toolkit for that? For that, we need to grab our polynomials. These are functions where variables are raised to powers. A quadratic function, where the highest power is 2, gives us that classic U shape, a parabola. That's the perfect shape for a ball being thrown through the air. A cubic function, with a power of 3, can give us even more complex S-curves. They basically let us model things that speed up, slow down, and even change direction. Now let's switch gears and think about a different kind of relationship. Like, how does the area of a pizza scale with its diameter? Or how does the force of gravity get weaker as you move farther away from a planet? This is all about scaling. These kinds of scaling relationships are described perfectly by power functions. They look like y equals x to the power of a. And that exponent a can be anything. It could be 2, like it is for the area of a circle, or it could be -2, like in Newton's law of gravity.
These functions are absolutely essential for understanding how one thing changes in proportion to another.
All right, let's move on to the next set of tools in our kit. These are perfect for modeling processes that unfold over time. We're talking about things that grow, things that shrink, and things that just keep repeating.
Think about a colony of bacteria that doubles every single hour, or the radioactivity of some substance that halves every year. The change isn't just happening, it's accelerating, it's getting faster and faster.
Now, what's so fascinating here is that a single type of function, the exponential function, can handle both that explosive growth and rapid decay. It all comes down to the base, that b in the equation y equals b to the power of x. If b is bigger than 1, you get that classic J-shaped curve of runaway growth. But if b is between 0 and 1, you get a decay curve that just plummets towards 0. So cool.
So far, we've looked at stuff that pretty much goes in one direction, up or down. But what about the tides coming in and out every day? Or the seasons changing every year? Or the vibrations that create a sound wave? How on earth do you model something that's cyclical? For that, we have the beautiful repeating ways of trigonometric functions. Sine and cosine are the absolute bedrock for modeling any phenomenon that is periodic. Their predictable, oscillating, wavy nature makes them the perfect tool for describing the natural rhythms of the world. So let's just take a step back and look at our whole toolkit. From the simple, straight line of a linear function, to the J-curve of an exponential, all the way to the repeating wave of a sine function. Each one of these families gives us a unique shape, a unique pattern we can use to describe a different piece of reality. And really, this is the big takeaway. These aren't just abstract ideas from a math textbook. They are the vocabulary and the grammar of the language that describes the world around us. Learning to see these functions in action is, well, it's like learning to see the source code of reality itself. So the next time you see a ripple in a pond, or the way a plant is growing, or the arc of water from a fountain, maybe just take a second look. You now have the basic toolkit to see the underlying mathematical elegance in all of it. So my question to you is, what are you going to discover?